is starting to.
Okay. So, okay. Welcome everybody to the October FPGA seminar, and today we have Tiwana and Tomasz Czajkowski from Intel PSG. Gurv is the manager of the device modeling group, and so he's going to tell us a little bit about what they're up to and where they're trying to get to.
Okay, thank you. Hi everyone. So my name is Gurvinder Tiwana. Some people call me Gurv. Tom, you might have met before. You call me Tom. So we're going to talk about what my group is up to, and Tom's going to talk about some of the work he's been doing recently on power optimizations. So, I manage the software device modeling team here in Toronto. I'll talk about some of the tools that we work on, and share some of the industry trends that are happening in the space of FPGAs and power, and then Tom will finish off talking about some power optimizations. So my team predominantly works on software tools for power analysis. So there's two main tools that Intel offers. One's called Early Power Estimator. It's a Excel-based tool, allows you to estimate power for your design. And then there's a Quartus integrated power analyzer, Quartus QPA or Quartus Power Analyzer. And that actually looks at your RTL and your net list and does more detailed analysis of power. The main things that our customers use these tools for is predominantly two things. One is thermal design. So how do you figure out what size and type of heatsink do I use on my application? And second is regulator design. So figuring out what regulators to pick and what sizes to pick. And in fact, FPGAs don't just have one power domain, they have over a dozen different power supplies. So actually designing the power tree for an FPGA is a non-trivial task. And so these tools help you with that effort. And lastly, of course, FPGA designers need to know what their power is so they can budget for it in their end system. So they use these tools to just budget for power. That's not the only thing my team works on. Another technology that we develop is signal integrity models. So for IOs that communicate to the outside world from an FPGA, you often find that you need to do link level analysis to figure out metrics like overshoot, undershoot, signal integrity, make sure that when you're communicating a 1 from the FPGA, it's recognized as a 1, and 0 is recognized as a 0. So for that, there's an industry standard spec called IBIS, IO Buffer Information Spec. It's a industry standard spec that all silicon vendors provide for their IBIS. And so my group also develops these models for Intel FPGAs. And lastly, power integrity, so power distribution network. So one of the challenges of designing a board that will house an FPGA is, like I said, how do I design the power tree that provides the power for the various domains that the FPGA requires? And one of the considerations you have to take into account is decoupling capacity. So a power supply cannot instantaneously react to current demand in the FPGA, and to solve that problem, you provide some decoupling capacitance on the board. But how do you figure out how much do I need for my application and for my system? And so that's again a non-trivial problem. We have a tool that helps users answer that question. It's called a PDN tool, or Power Distribution Network. So a little bit more about PDN analysis. As mentioned, stands for Power Distribution Network. Some of the trends that are happening in the space, as I don't know if you can read that chart there, but it's pretty old, from 1990 to 2000. But it's basically saying, as power consumption goes up, the voltage supplies, traditionally they were going down, but they've kind of stabilized now. So the power supply, you notice on modern FPGAs or even ASICs are not shrinking or lowering as fast as they used to. And if you just look at the required impedance to maintain some sort of voltage at the load or the FPGA or an ASIC or any device, that target impedance is going down. And so that creates a problem for designing your power distribution that becomes more challenging because you now have to target a lower impedance. And so you notice that with our FPGAs, as you use some of our advanced FPGAs, it can be a challenge to design a power distribution network that is robust to supply all the current requirements that you need for your application. And so again, this is one of the reasons why we need a tool to help customers with this problem. Okay, so diving more into power analysis, because that's kind of the meat of what we're going to talk about today. I mentioned Cordis Power Analyzer. It's embedded in our Cordis suite of tools, and it looks at your RTL and your design and figures out the power in the end. But it has techniques to figure out toggle rates. So some of the ways you can get toggle rates into this tool is, one, we have heuristic algorithms for vectorless toggle rate estimation. So just looking at your RTL, looking at the primary inputs, and propagating that information to each node in the design to figure out how often certain nodes will toggle. That's one of the key things you need in order to do a power estimation for a design. And so this tool has a built-in vectorless engine to solve that problem. The other thing you can do is import simulation vectors. So if you have a functional simulation of your RTL, you have detailed waveforms of how signals are toggling throughout your design, you can import that information into the tool to get a more accurate, precise estimation of power. And finally, because this tool runs after placement and routing, you know exactly how much capacitance you're using for your routing and clock networks, and so you can precisely figure out what the power of your application is. So that's the Cordis integrated tool. The early power estimator, or EPE for short, is a standalone tool outside of Cordis. You can download it from our website. And to use this tool, you don't have to have RTL. So designers that are just starting off and starting to architect their overall system often use this tool to figure out quick and dirty ways of doing power estimations for their end FPGA application. And so, to get a power estimate, you still need to provide some resource estimates and toggle rates. So you provide that information, the tool will estimate the power for you. And I kind of alluded to this already, but if you look at different stages of FPGA design and when various tools are used. So early on, one of the first things that our end customers do is figure out what FPGA do I need for my application. And so in that stage, they often consider power because do I want a high-end FPGA, a mid-range, or low-end? One of the considerations is how much power can my system tolerate. And for that, an EPE tool is ideal. You have a tool, you can do what-if analysis. If I use this device in this environment, what is my overall power? So it's a quick way to assess and narrow down your device selection. And then RTL. So then they start actually coding up RTL. But oftentimes with modern FPGAs, it's not just one FPGA customer building the entire system. There's someone writing RTL, there's someone designing the actual PCB, and they're often working in parallel. And so in this stage, the PCB designer, even though the RTL is not finished, needs to start building up the PCB, and so they use the early power estimator to get early estimates and figure out the scope of what they need to design for on the PCB side. And so again, they use EPE for that. And once they have an RTL, push it through Cordis, and run post-fit or run the actual compiler through Cordis, you can at this stage run Cordis Power Analyzer. And so at this stage you can get you can use vectorless, you can use vector simulations to get a detailed power estimation for your design. You can compare it to your early estimate and see and compare and make modifications to your end system. And finally, once you get to silicon, customers can continue to use our tool, or they can actually get a power estimate from their actual silicon setup. And oftentimes with FPGA design, users don't just have one programming file that is their end system. They have multiple variants testing in parallel, and so oftentimes they find you just program on board and get a power estimation exactly at that stage. So this is kind of the life cycle of a typical FPGA design. Okay, so talking about some of the trends. Why are these tools becoming more and more relevant? What's driving some of this focus on power? So I pulled up this data from Wikipedia, and this is just Intel CPU power over time. And so it's kind of a busy chart, so let me walk through it. So on the x-axis is the various Intel CPUs, starting from the Pentiums, Pentium 2, all the way, it's kind of an old slide, Core i7s a few years ago. So the red line is the technology node, and you can see, as time's gone on, we've moved on to newer and newer nodes, and we're down to latest technologies are in the 10 nanometer range. And the other interesting thing to look at is clock speed. So if you remember in the early 2000s, you bought a computer, if you waited a year, you would see clock frequency go up, 1 gigahertz, 1.5, 2 gigahertz. And that trend continued for a while, and then it kind of stopped. Now these days you see a CPU not more than 3 gigahertz usually. And why is that? So you see the clear trend, the green line went up, and then it kind of just tapered off and stopped. And the key insight there is, if you look at the purple line, which is the power dissipation of these CPUs, they steadily went up as clock frequencies went up, and then they kind of hit somewhat of a wall at about 100, 150 watts range, and they kind of stabilized. So that's the key thing that changed the way CPUs were architected to not just focus on pure clock frequency and be limited by the amount of power that you can actually provide into the compute. And if you plot an analogous trend for FPGAs, you kind of see the same sort of trend happening. So it's kind of a different plot, but let me walk through it. So you have density again with the triangles, the various process nodes that Intel FPGAs have been developed on, and the blue bar, which is the power dissipation. This is I'm using some assumptions here because FPGAs, depending on what you program, the power can vary drastically. But if you use a consistent set of assumptions, you'll see a trend emerge that power dissipation has gone steadily up. The reason it bounces around is we have low-end FPGAs and mid-range FPGAs, so it's not fair to compare all of them. But if you just look at the overall envelope, you can see that power dissipation has gone up considerably. And the driving factor for FPGAs is not necessarily frequencies, which have also gone up, but just the sheer density and size of the FPGAs have gone up tremendously. Plotting on a logarithmic scale the amount of logic elements in an FPGA from 2 decades ago to now. You can see we're at the 5 million LE range now with our modern FPGAs. So that complexity and the size has a demand for power, and so our power dissipation has gone up alongside that, and that leads to the analogous question on CPUs that we went up to a certain point and we kind of hit a wall and we were limited by power, and we're kind of getting into that zone with FPGAs now.
Good. I guess a question on, so is this the largest FPGA, fairly full, running at a reasonably high clock frequency? Like how do you generate the numbers?
So, taking each of these FPGAs, 80% full, running at the target frequencies that we expect customers to use in that application. So again, it's an assumption.
So a typical clock frequency the customer achieve 80% full is like the largest device in each generation.
Yes. So both of those plots kind of point to this phenomenon, which you see in literature, power wall. As your frequencies go up, your power dissipation goes up, your cooling costs and operating expenses go up alongside, and there's tremendous pressure to reduce power and manage the power dissipation of your end system. I pulled up some metrics. ICT, Information and Communication Technology. This is a subgroup of, subcategory of CO2 emissions. If you guys, read the articles, CO2 emissions are tracked yearly into different categories: aviation, transportation. ICT is one of the subcategories, and this is all things semiconductors, right? Data centers, CPUs, and so forth. And right now, ICT is 2 to 4% of global CO2 emissions, and just perspective, that's equal or comparable to worldwide aviation. So that it's not negligible. I mean, it seems small, 2 to 4%, but that is considerable if you look at the scale of things. And it's also one of the fastest growing sectors. So the concept of green computing or wasteful computing ties into CO2 emissions, just like driving around wastefully, right? But the irony is, because we're pushing the envelope on getting smart connected devices, some of the technology in ICT can actually help reduce CO2 emissions in other sectors like transportation and manufacturing. So it's not all bad. Power consumption for the sake of compute is not necessarily a bad thing. We can actually reduce it in things like Uber, where you can save fuel costs and transportation times by using smart technologies. So, but what does that mean for FPGAs? So, we know power consumption is going up, operating costs and cooling expenses are going up. What can we do to help FPGA designers manage power in their systems? So, we need to help them design efficient RTL. And depending on how you put up your RTL, you can have drastically different power demands for the FPGA. There's automated things we can do, like in CAD, when we're taking RTL and compiling it down to an FPGA. There are techniques and algorithms we can use to help optimize power. And lastly, users can't do this, but when we're designing FPGA architecture, considering power and putting in features that allow you to manage power dissipation at the architecture level. And all of these things require some level of power models and power analysis. And so this is the crux of what my team looks at, right, when we look at power model and power estimation. So talked a lot about power, but power goes hand in hand with thermals. So what is thermal analysis? At a high level, what you're trying to do is two things. One is make sure your cooling solution that you provide to your end system is sufficient to dissipate the heat generated by the device. And how do you do that? You make sure that your junction temperature, so the temperature at any point on the die, doesn't exceed whatever the device specifications happen to be. And so, as a thermal designer, you need to make sure you guarantee these two things. And how do they do that? So, there are industry standard tools out there that you can do a detailed 3D thermal analysis of your entire system, tools like Mentor FlowTherm or ANSYS IcePack. But what about FPGA designers? So we've added basic thermal analysis capabilities into our power analysis tools as well, which can help you estimate the junction temperatures at various parts of the package. So I won't go into the details of that, but that's a capability built into our power analysis tool. That's not what it looks like on my other animation. So I'll end off and give Tom, hand it over to Tom to talk about some of the power optimization work he's doing. But just finish off by saying, FPGAs, as you guys might know, are increasingly being used to accelerate workloads in applications like the cloud and data centers. This type of application for FPGAs, why is that happening? One of the reasons is FPGAs offer a superior performance per watt over competing technologies. And as users start using FPGAs in this way, they are more sensitive to power, and they need software tools and analysis to help them trade off performance and power so that they can manage and actually achieve the advantages that FPGAs promise, which is superior performance for what. And so some of the work Tom has been doing in this space is going to talk, he's going to talk a little bit more about that.
Can I ask you a question?
Sure.
So 100 watt Stratix 10 power dissipation. So how are FPGA customers reacting to that? Because that is a much bigger number. So both in the data center, because the new customers, and in the traditional embedded computing space for FPGAs, how are they reacting when you go out and show them that number?
Yeah, so you got to remember, Stratix 10 is not just one part. I showed the biggest one. There is a spectrum of parts that are much smaller, and obviously the power is not 100 watts for those parts. And so some of the niche applications are often not using the biggest, most powerful Stratix 10 FPGA, right? Some of the bigger FPGAs are typical applications for those are ASIC prototyping, for example, where it's a different application altogether. So my answer to that is yes, it's a mindset change, because traditionally when users thought about FPGAs as 10 to 20 watts of power, it's not the heart of the system. So power and thermals were not really the top consideration, I would say. But definitely as we are heading down into our latest and greatest FPGAs, that mindset is kind of shifting, and that's kind of what's pushing some of this research and investment into what can we do to help customers manage through that.
Thanks.
I just have a follow-up on that. I'll say the 100 watts, is that in gigabit transceivers, or is that in a hardened on-die processor, or is that the core logic fabric?
So that's total. So that's.
Do you want to comment on how much of that would be in, say, I/O power consumption?
I would rather not. But here's a plug for our tools. You can go use our EPE, play around with that, and you can get a feel for where the power is going.
Right.
Okay. So, as Gurv mentioned, power is an important topic to consider. So just to give you a little bit of background, prior to joining Gurv's team this year, I spent about 6 years working on high-level design tools, and we've been working on enabling customers to be able to take the algorithm and put it on an FPGA. So as we produce bigger and bigger devices that provide more capabilities, one of the questions that came to mind is, could we help customers reduce the amount of power that they use in these kinds of designs? So that was basically the first question I got, which was, well, high-level design very well. Go figure something out. So where did I start to analyze this? So one of the things that I did very early on is to look at where the power goes. So I took one of my favorite applications, which is single precision general element matrix multiply, and I ran it on an ARIA 10 development kit. So that's an ARIA 10 with a 115 part, so that's the largest ARIA 10 part. And I implemented that design using OpenCL. And then using the power monitoring tools available on the board, I basically tracked where the power goes. Now, I've actually, in this particular case, run a matrix multiplication many times, so I get a very nice and steady power in the middle. But here's the breakdown of what each of those sections mean. So in an OpenCL application, what you have is a portion of the time that's spent taking data from a host and downloading it onto the FPGA. So that's in this download section right here. So as you can see, what's really happening here, some power is being dissipated, but it's not really for the computation purposes. It's just facilitating transfer of data from a host PC to the memory on the FPGA itself. So this is why you're dissipating some power on the IOs and the transceivers. Eventually, you get to the point where you say, now I want to compute my matrix multiply. So this is where you see power starting to increase, and this is where the computation is actually happening on the FPGA, exchanging data with object memory. And eventually, once you're done, hopefully the user cares about the result of matrix multiplication they just performed, and they will want to upload the data back from the FPGA device onto the host. As you can see, we've got some power for the transceiver, some power for the core. Here it's increasing. So the question is, could we do better, and what kind of tools do we have today to address that? So today, the focus of the tools that FPGA companies provide is a transformation from a register transfer level to a bit stream that allows you to program an FPGA, and that's where most of the optimizations happen. So at a high level, the way this works is you start with an RTL description, you go through synthesis where power modeling also happens, and you can optimize the design to reduce the power, estimated amount of power based on what your logic structure looks like. Once you have that, then you go through the fitting stage where you're actually trying to place and route the design. Again, considering how the design works, you can optimize for power and make sure that your average power is reduced. In the Quartus toolchain, we do have two modes that enable you to do that. One is the high effort mode. The objective of it is to reduce the amount of power that you're dissipating, but the goal is also not to sacrifice any performance. So it will do as much as it can, but it won't sacrifice performance. And a lot of the optimizations are kind of in a fitter stage. And there's also an aggressive mode where you're actually going to save quite a bit more power. Now, some Fmax may be lost, but you're usually saving a lot more power than you're losing in terms of performance. Now, if you're a designer, one of the things you would think about is this the only thing that I could do to optimize my design? So if you look at a system design holistically, you'll actually find that there are three general categories in which you can perform a design optimization. So I did not invent this. This is actually in the literature, so I can give you references afterwards. But there are basically three stages. So one is the conceptualization stage, which from a perspective of an architect is where you design what your application is going to look like. You will figure out how you partition your software and hardware, what's supposed to be running on an FPGA, what's supposed to be running on a processor, and then figure out what is the impact of those decisions on power. Now, in that particular space, Gurvinder already mentioned a tool called Early Power Estimator. So this is where you could actually figure out what your breakdown of the design is going to be and figure out how much power you're going to dissipate. Now, once you have made that design and figure out what your architecture is going to be, you go to the implementation stage, which has been the meat of FPGA tools for many, many years. And that's where you implement your design and you transfer your RTL description into bitstream. So here's where we have a tool called Quartus that basically allows you to do what I described in the previous slide. Finally, at the very end, you've got the runtime management. So that's a reasonably unexplored, at least for FPGAs area, where what you're really looking at is managing the amount of power and managing the performance of your system when it is actually on the board. Okay? So knowing things such as when the design is actually running versus when it's not running enables you to actually decide, do I or do I not want to spend power on that particular space. Now, for the most part, for FPGAs at least, there aren't too many tools, but there have been some recent works, and I want to call Devon and Ibrahim's work in dynamic voltage scaling in this particular space, which is really, really good. So if you haven't read their paper, it's very interesting. Go ahead and read that. Okay, so now if you look at each of those three spaces, the question becomes, what could you do? So what I wanted to do is kind of give you an overview of some of the things that you could try out. So starting at the conceptualization level, one of the things that I would mention is that we do have, today, high-level design tools. So what do they bring to the table? They bring to the table the ability to look at and explore various architectures for designs. Now, once you have that ability, what you can do then is, say, include power optimization at that design stage, allowing an architect to basically explore more and more architectures and pick the one that's better suited for their application and consider power in there. So what I did here, and I apologize for a lot of code, but basically I showed part of the algorithm, which is actually an FFT algorithm. And in that particular case, there are some pieces of code that are triggered by flags that are supplied to a kernel or an OpenCL application. And as it turns out, in this particular case, they're sometimes used and sometimes they're not. Now, if you build a circuit that you always compute all of the equations in these if statements, then you're actually consuming power, but you're not actually getting anything out of it if the transpose and the manual bits are set to 0. So an example of what you could do, and I just at the high level describe how this could be synthesized, is you could say, well, if I want to implement these if statements, I would basically implement all of them, compute both, and then depending on which case of the if statement I'm going to take, I'll just multiplex them out. For obvious reasons, you're actually spending quite a bit of power computing both sides, but if you could prevent that from happening, you could actually reduce power by roughly 30%. And that's a made-up example. So an interesting ways to do that would be to simply put registers on the input and make sure that you will only allow transitions that affect that path, knowing that that's going to be your result, to be propagated outwards. So you're not actually taking any part of the circuit out, you're just making sure that the transitions and the amount of power spent on the computation is reduced. So that's at a high level. At the core level of FPGA tools, we have power-driven place and route. So this has been in Altera's tools for a while. What it really does is it allows you to optimize how the design is placed and routed. So here's a simple example where you've got a couple of blocks that are driving the block in the middle, and depending on how many transitions per second you have on the routes, you may want to move them left or right. In this case, you want to move them right to reduce the capacitance on the wires and therefore reduce the amount of power you're dissipating. Similarly, you want to optimize the clocking network, so that also happens automatically in the Chorus tool channel. Now, the last part I wanted to talk about as well is this idea of runtime management. So Vaughn's work is a seminal work in that category for FPGAs. So I'll talk a little bit about different strategies. So in some cases, you may have applications that are not necessarily limited by clock frequency. What does that mean? In a system, you usually don't just have an FPGA. You will have some sources of data, some communication interfaces that allow you to exchange data with the outside world. If the I/O interfaces or, say, memory bandwidth is limiting your performance, then you could possibly be running your design at a much faster rate than it is useful to process that data. So what I've drawn here is an example where, as you're scaling fmax, your throughput should be increasing, but in one mode, you're limited in terms of performance by, say, memory at this point, at another you're limited at this point. So depending in which mode you're running, you may not necessarily want to run at the same clock frequency. So that actually happened to be the case in one of our FFT benchmarks. So it's a simple benchmark application that, it's reasonably small, but it is representative of what you could do. I was running it at about 287 megahertz, and it had exactly two modes. So the way that this worked was, it was always computing in FFT, but in one case scenario, the way it was reading memory was not in a streaming fashion. In another case, it was in a streaming fashion. So what you can see is, in a non-streaming fashion, your throughput was about just under 20 gigaflops. In a streaming fashion, you were around 61 gigaflops. Mind you, we're not really filling a device here, so this is not the top capability of the device by any means. So then what I did is I actually said, okay, well, if I'm running in mode 2, this is definitely where I want to be in terms of performance. But if I'm running in mode 1, all I'm doing is really spending quite a bit more power than I really need to. So what I did is I was able to switch the clock frequency for that particular mode when it was running, and then see that the average power while in that mode dropped by a couple of watts, but my performance did not. Okay, so what's on the table is, are there a lot of opportunities for us to do research? And some research has been done. I've spent quite a bit of time looking at research both on FPGAs and on ASICs and various technologies. So there's a lot of work in this area for FPGAs, but not so much in conceptualization and runtime. So this is a citation to UofT right here. I just copied the results. But basically, there's quite a bit of work that could be leveraged, that exists, and could be commercialized. There is quite a bit more research that could be done in each of those areas, and it's an important step. It's an important step to take. So, as a conclusion, my takeaway is, well, power research is on the rise, or if it isn't, I invite you to help make that happen, so that power research actually is on the rise. And there are lots of low-hanging fruit to help us improve performance per watt metric, or enable us to get more performance per watt of power in any FPGA designs. So just to highlight a few areas, high-level design optimizations are fertile ground. There have been just a few papers that talked about tools like HLS tools that would optimize for power, but not as many as I would like to see. Runtime management is reasonably unexplored, as I mentioned. Again, another fertile area. In the core FPGA algorithm, so that would be the core quartus, place and route, synthesis, there's quite a bit of work to be done, However, you cannot really expect massive gains because some work has already been done. There's been a lot of effort on that. So you should expect difficulty attaining gains, but those are still possible. Okay, this is it for my talk. If you have any questions, please feel free to ask.
In your prior chart, it looks like you're assuming dynamic power is roughly equal to static power. Is that,
In which chart?
go back one chart. So the power reduction is performance per watt improvements are basically
Yeah.
half the dynamic power reductions. So does that mean that in Stratix 10, approximately half the power is static?
No,
That?
no, and I would not comment on the breakdown. Also, that would be one of those things that's design dependent. So perhaps an additional explanation to this chart is when I was studying various works, often enough you'll find that an authors will publish, we've saved X amount of power, and they very conveniently omit the performance of a particular benchmark. So it is very difficult for you to figure out where you would sort of be. Sometimes they'll tell you the clock frequency, but that's not always representative of throughput. Just because you linearly increase clock frequency doesn't actually mean that your throughput increased linearly. It really depends on what your application is actually limited by. So in those cases, I basically look at it and say, okay, well, based on what this paper is saying, it looks like it would be about this. So that's more of a guesstimate. In some cases where I would say NA or not disclosed, basically there was absolutely no information for me to make any kind of inference. In some cases there was, such as in your work, there was a clear performance per watt chart that showed exactly where we are. So that's something you would look at directly. Partial configuration example, also there was a performance per watt metric. It was easy to ascertain, but in some cases it was unfortunately not as clear.
So as I was saying, if I just repeat that back, that two things are affecting it. There's static power as well as dynamic, but also there's some of these techniques have reduced performance. So,
Yes.
so I shouldn't interpret it as the 30% dynamic turning into a 15% performance per watt. Some of that could be because of clock frequency drop.
That's right. That's right.
I think Stratix 10's early power estimator is not yet public. Is that correct?
That is correct. Yeah.
So that makes me, I guess, want to ask that question. You switched to FinFETs. What did you do to static power versus dynamic power? For quite a few years, my rule of thumb was for a high performance design, around 30% of your power would be static in most FPGAs and 70% dynamic. I mean, most high-end FPGAs.
Yep.
Is that a reasonable rule of thumb for Stratix 10, or has it changed?
So it's not that simple anymore. One of the features in Stratix 10, this is public information, is something called Smart P.H.D, which means at manufacturing time, the actual voltage that the FPGA requires is programmed on a per chip basis. And so to power up with a Stratix 10, you need a smart regulator that looks up what voltage does this chip need and then provides that voltage. And so the same application running on different chips would actually have a different mix of static and dynamic because the voltage is changing. Right? So it's no longer safe to say static is always 50% or 40% or whatever it is. It actually varies part to part for the same application. Yes, so EPE is not yet public, but it will be in, I believe, in the next month or two. We're going to make that public. So that's all I can say about that.
Would you say people should target, if you're working on a power reduction technique, should you be targeting dynamic? Is it still dominant? Static because it's become dominant, or it's just a mix?
I think the biggest knowledge, is this runtime management, right? Taking advantage of the inherent knowledge of the application and looking at the actual trade-off of performance and power for that application. I think that's probably the biggest advantage or biggest knowledge we have, and it looks like, according to Tom's research, that was the biggest lever that we found.
So for the OpenCL compiler tool, does it currently use different clock domains based on how much, some kernels might have a disparity in data consumption or production and can be clocked lower?
Not at the moment, as far as I know.
So what you did with your experiment, that was first of all, that was during runtime you switched it, the PLL, or?
That's one way to do that, yes.
Okay. So
it was a bit more trickier.
So currently, that was like manual, just an experiment in what
Yeah.
can be done.
Exactly.
What's the granularity of the smart PID feature on Stratix 10? On ARIA 10, I believe it's just 2 voltages for two temperature classes. So like if it goes below 10 degrees, then it will run at 0.85 volts, and if it goes above that, it's 0.8. Is that the same for Stratix 10? And is that accurate?
So I'm not sure if that's fully accurate for ARIA 10. Yes, you're right that as you go below a certain temperature threshold, will raise dynamically for ARIA 10. So what I can say is Stratix 10 is more granular than ARIA 10. I'd have to go look it up, but I don't think ARIA 10 is as coarse as you just described it. But Stratix 10 will be more.
Any other questions? No? Okay, go ahead.
Sorry, I believe, correct me if I'm wrong again, but for ARIA 10 there's just one T diode, and you were talking about temperature analysis across the chip for Stratix 10. Are there more sensors on Stratix 10?
So you're right. One way to do temperature analysis is to actually measure on the actual chip, right? And for that, the more diodes you have, the better. But the other way you can do it is through models. And so what we have in our software tools is our models of how thermal heat is transferred within the chip and within the package. And through those models, you can estimate what the junction temperature at various places would be. And for locations where there is a temperature sensing diode, we can give you, an offset, or we can tell you at that location what our models predict, and you can just go see, at that location what the actual temperature is. And so I won't answer the question how many diodes there are, but we have models that don't necessarily rely on having more thermal sensors.
Just in the planar process technology, you had the body bias that you could use for producing leakage, and you had the lab-wise, I forgot the commercial name for it, but you could
High speed, low power.
The high-speed, low-power concept in some previous Altera families, but I guess with FinFETs, the body bias option is not there. Could you comment on the static power, ratio that you're seeing in the FinFET Stratix 10 versus in planar, traditional planar CMOS?
So I won't be able to divulge the actual numbers, but EPE is not yet public, as Vaughn mentioned. So you're right. So we used to have body bias in ARIA 10 in previous families.
Right.
We don't have it in Stratix 10. I think this is public information. But what replaces that is the thing I just mentioned, smart BID, where you're no longer controlling the static power within local regions of the FPGA. You're controlling it at the chip level. So if you have a fast part and you have some margin on performance, you can lower the voltage to save static power and dynamic power.
And that's set once at a time of manufacture. It can be adjusted for aging later on, or it's just set once?
It's set once, but there's an algorithm for things like as it monitors temperature, it can react to that dynamically.
I see.
So I forgot my question at the end of that. So I'll see what comes to you.
Okay, Andy. Yep.
You mentioned smaller SKUs for Stratix 10. Does static power go down with those, or the smaller chips? Like,
yes.
So are those actually physically smaller dies?
Yes.
Or,
so the density is smaller.
Okay.
Now I remember my question. So you're calculating junction temperature across the die with a 2D thermal model, I guess. What use are you making of that? Are you using that to check for hotspots and say you've got a problem, or are you also using it to calculate static power, where you're taking into account local temperature gradients?
Both. So what we're trying to help customers do is, one use case would be a customer tells us, please make sure that no point in my package goes above 100 degrees C, and we'll take that as a constraint and ask what is the minimum amount of cooling do I need to ensure that happens, and that will take into account the 2D models that you just described to make sure the worst case hotspot given this application doesn't exceed 100 degrees C, and what's the minimum cooling I need for that to happen. So,
And when you calculate static power, you also take into account
Exactly.
the local hotspots to be more accurate.
yes.
Do you see an opportunity to, there have been some research papers that have looked at power driven placement rather thermal driven power placement rather. So they try to spread out the thermal hotspots.
Mhm.
Do you see much opportunity for that, or do you think the hotspots are largely just, they're around the transceivers and around this hard block and there's not that much you can do?
Yeah, so it varies from architecture to architecture, right? Like hotspots are dominated by power density, right? So you're right, high-speed serial IOs tend to be more power dense than for FPGA fabric, for example. But that may not always be the case depending on the architecture, right? So it's hard to say a hard and fast rule. But for data center applications, that is an interesting, we need to know that because you don't know upfront what workload you're going to be accelerating. So you don't really know where the hotspot's going to be. So whatever you can do to mitigate that or control that, I think it's, would be applicable.
Just out of curiosity, like for EP and FPGA, what's the estimate? Generally, what's the difference in this percentage?
Yeah, so early power estimator is standalone tool. It doesn't have any access to your RTL. So one of the things that I would say the biggest knob that impacts accuracy is the fidelity of the input. So if you enter unreasonable clock frequencies and utilization, you're going to get garbage out, right? Garbage in, garbage out. But if you use a flow where you compile your design through Cordis and export, we have a flow where you can export through Cordis a profile that you can enter into the EPE. With perfect information, in our benchmarking, we see about 15% difference between the two.
Okay, so, all right, let's thank the speaker. Okay, and we have pizza thanks to Eberts, and thank Manuel on the